Hello, I'm a researcher at PortSwigger, the makers of Burp Suite, and I'd like to share with you today some of the research that I've been working on. So, welcome to Portable Data Exfiltration, XSS for PDFs. In this talk, I'm going to show you how to booby-trap a PDF document, track when a PDF was opened and closed even when loaded from a file system, and exfiltrate the contents of an unknown PDF on both Chrome and Acrobat. All these techniques use a PDF injection. My colleague James Kettle was watching a Black Hat talk about PDFs, and he was looking at the code and thought to himself, this looks injectable. And he got back to the office and we had the following conversation. He said, PDF code is totally injectable. And I responded, I think it's impossible. You wouldn't know the structure of a PDF. The XREF table would break, the objects would break. How could this be possible? But that didn't stop me there. I then began to test for PDF injection. So we're going to cover injection theory, how user input can get inside PDFs, why you just can't inject arbitrary content. I'll talk about my methodology, the vulnerable libraries that I encountered, and then we'll go on to exploiting injections in Chrome and Acrobat, as well as a hybrid injection. Then I'll wrap up with defense, leaving 5 minutes for questions. Server-side PDF generation is everywhere. It's in invoices, in receipts, in e-tickets, in payslips, in boarding passes. The list is endless. So there's plenty of opportunity to get user input inside a PDF document. If you imagine a PDF injection as an XSS injection, and imagine you're injecting inside parentheses, this is very similar to what happens when you're injecting inside PDF code. Like JavaScript, you have to ensure that the syntax is valid. This means repairing the parenthesis before your injection as well as the parenthesis after the injection. A PDF is structured into objects, XREF table and trailer. There are more parts to it, but just for the purposes of this talk, I'm going to focus on these 3 parts. So the objects allow you to define text streams and images, for example. The XREF table contains a list of all the objects in the document, and the trailer appears at the end of the document that defines the root object. So this is what an object looks like, very simplified, in a PDF document. So this is the first object indicated by number 1, and the revision is 0, and the OBJ is the start object marker. Then we have the start of a new dictionary, and we have a dictionary key here, in this case pages. And the value of the dictionary key in this instance is 2 space 0 space R. This indicates it's a reference. So it's looking for the second object, revision number 0, somewhere in that document. So the pages dictionary key allows you to define the amount of pages in the document, and in this instance we're using a reference to the second object which will define that information. And that's the end of the dictionary here. This is the XREF table. It begins with the XREF keyword, and this is the first object in the XREF table, and that begins at position number 10. So at the 10th position in the document is where the first object begins. And using the start XREF keyword, this will tell you where in the document the XREF table begins. In this instance, it's at 413. So I'm going to talk about parsing briefly, just so you can understand how the PDF document is parsed. This doesn't contain the whole thing, just enough information for the talk. So first, the start XREF is read, and it points to the XREF table. Each of the objects is then read in the XREF table, and then all the references are followed. Our most likely injection point might occur in the objects themselves. and then the payload is executed inside the object, and then the document is rendered. So one likely injection point is in a text stream. So here we define an object, which is object number 4 with a length, and it's a stream, and BT indicates the begin text. We define the font and the font size, and then we define the text itself, which is hello world. So an injection could occur here. So you can inject here, you could inject a closing parenthesis, for example, break out of that code and allow you to define a new object. But the problem we have here is we can inject a new object, but the XREF table wouldn't be updated. So that object would never get rendered. So you could see why I thought it was impossible to do PDF injection. But this is annotations, and annotations are great. They allow you to define a link anywhere in the document. So you create a new annotation, you give it a rect, so like the rectangle for where you want on the page to be clickable, and you give it a URI dictionary key, and our injection can occur within the parenthesis. So now this is interesting. So because we can break out of the parenthesis here, we could define a new annotation, like update the annotation with the annotation array with a new entry, and then we could inject our own annotation and then execute what we want. So this is what makes PDF injection possible. So I was testing around 8 different libraries, and I came up with the following methodology to test them. Identify, construct, and exploit. So first you identify, can you inject parentheses or backslashes? So a library should escape parentheses and backslashes in URI dictionaries or text streams. If they don't escape any of those characters or one of those characters, then there could be PDF injection in the library. I also tried multi-byte characters, for example 5C29, which is the backslash and the closing parenthesis. So the idea here would be to inject a multi-byte character. The library would then convert them to single byte characters, which then may allow those dangerous characters to cause PDF injection. I also tried things like ASCII range overflow, so adding a character over the ASCII range that might get converted into another character like parenthesis or backslash. I also tried causing errors in the PDF rendering process by injecting nulls or end of file markers or comments. Once you've identified that the library is vulnerable, then you can try and find a site that uses this library. So then you need to construct a PDF from the injection that has a callback by either calling alert 1 if you know the structure of the PDF and you can render it, or a callback by using the submit form function, which would post to an external URL. This would be useful in blind situations where you don't know the structure or content of the PDF, but you can still cause an injection. Also, with clients that do not support JavaScript, you can use the submit form action and also do a callback. So once you've identified that your PDF is rendered and you've got a callback, then you can exploit it. And you can exploit it by stealing the contents of the PDF using JavaScript, or without JavaScript using submit form actions. So I tested around 8 different PDF libraries. And the first one that I encountered that was vulnerable was PDF-Lib. This has over 52,000 weekly downloads, and they made a crucial mistake. So this JavaScript generates a PDF document using their library, and they made a mistake in the PDF string helper. So if we zoom in, the URI of the annotation is defined here, and it uses the PDF string of helper. and we can inject into this helper, and you can inject parentheses, and the parentheses aren't escaped. So this allows you to inject code into the annotation and define your own annotations. The next library I encountered was the JS PDF library. This has over 250,000 weekly downloads, so it's quite popular. And they made a similar mistake. So here we define some JavaScript that generates a PDF with an annotation, and that annotation has a URL property when you create the annotation, and that URL property is also vulnerable, similar to the other library that I showed you, so you can inject parentheses and inject your own PDF code. So now I'm going to talk about exploiting the injections on Acrobat. So this is the alert one of PDF injection. I use this as my base code every time I wanted to improve upon what an injection does. So first we break out of the PDF string. The grey code is the existing code. The black code is actually our injection. So we break out of the PDF string. We define a new action, in this case JavaScript action, which will call some JavaScript that we define here. So this calls app.alert1. And then we repair the existing action using /parenthesis, which allows you to create valid syntax in PDF and doesn't cause it to break. But there was a couple of challenges with, so I could call JavaScript, but there were some limitations. So you could only have a limited selection of objects with the Acrobat JavaScript. You couldn't read cookies, for example, and you have no access to the DOM at all. So you couldn't do document.body or document.body.innerHTML, for example. So you're very limited. Although you have JavaScript execution, you only have a limited selection of objects. But how about we exfiltrate the entire contents of the PDF? Because we might not know the contents. It might contain something sensitive, so we can extract the contents of the PDF using this technique. So first we inject app.alert1 to confirm the injection occurs. So this is using the alert 1 of PDF injection I mentioned before. Then we use the submit form action as mentioned here. This makes a post request to a URL that we specify. So this function accepts a string, like you can specify an external URL as a string, or an object, which in this case we're using an object. So we supply an object with a CURL property that specifies an external URL, which in this case is the collaborator URL. And we have the CSubmitAs property, which allows you to submit the entire contents of the PDF, which is pretty cool. You can also do this without JavaScript, which I thought was really nice. So you might encounter a client that allows you to execute, that doesn't allow you to execute JavaScript, for example, but does allow you to use submit form actions. So this becomes in really handy for that instance. So I removed all the JavaScript from the alert 1 vector and then added a submit form action and gave it a flags dictionary and a value of 256. Now in the PDF specification, you can use the 256 value to submit the entire contents of the PDF with the submit form action, which is pretty cool. You can also booby trap the entire PDF document from an injection, which is nice. So here we inject a separate annotation. So rather than reuse the annotation that we've got already, which might only be a small area, we inject a new annotation so we can define our own clickable area. And then we use the rect dictionary key to specify the rectangle for where this is clickable. So it accepts the X and Y coordinate as well as the width and height. So we make the entire document clickable so the PDF is booby-trapped, they click on it and then we can steal the contents of the PDF. We use the existing parenthesis to complete the injection. On Acrobat as well, we can execute automatically, which is really awesome. So here we inject a new annotation, we specify a rect so we can get a clickable area, and then we specify the PV dictionary key, and this will execute this annotation when the document is visible. So this is really powerful. We don't even need to booby trap the PDF now. All we need to do is get the victim to open the PDF and it executes automatically. You can also do the same when the PDF document is closed. So we can track when the PDF document is open as well as when it's closed. So this uses the PC dictionary. So this executes when the document is closed. So when testing for PDF injection, I thought, what would be the shortest possible XSS vector, or the PDF XSS vector, should I say? And I managed to reduce it quite a lot to the following. So here we use the existing PDF action, we break out the parenthesis, we add our JavaScript action and execute alert 1, and reuse the existing parenthesis to complete our injection. So this is really cool because you might have a length restriction, for example. So the shorter we can make this code, the better. So then after exploiting injections in Acrobat, I thought, how about when the PDF is loaded from the file system? How is that different? Well, when it's served from the file system, there are a couple of challenges. So post requests are blocked. The user actually gets a prompt whether to allow or deny that post request, which is not ideal. We don't want that. But can we still make a request? Well, I decided to write an enumerator to try and make a request without a user interaction. So I wrote an enumerator. So I wrote a for loop that looped through all the objects in the Acrobat object. I skipped like the norm functions that cause a prompt, such as get URL and submit form. So I looped through all the objects in the global PDF object, and I called every function of every property in every function, and passed a collaborator URL to all those functions and waited for interactions. I did this for 3 levels deep, so I did like 3 for loops that all called every function with a collaborator URL, and I found a function. It's called CB shared review if offline dialog. That's a mouthful, but it's awesome. It makes a request. So I was really pleased. So this dialog makes a DNS request regardless what option you choose in the prompt. Awesome. So I can track if you open and close the PDF from the file system via DNS. This is really nice. I can also exfiltrate the contents of the PDF via DNS. And this is what the prompt looks like when you call that function. So it makes a DNS request to the collaborator server where you can see it's return the reverse DNS of the collaborator server, and it gives you a prompt: work offline or keep trying, and it doesn't matter which you click, it will still make the DNS request even from the file system. So that's quite scary, really. When you open a PDF from the file system, it can be tracked when you opened it and viewed it and when you closed it. So that is pretty scary. So then, after my success with Acrobat, I started to check my injections on Chrome. but I was disappointed. All my injections failed. So I decided, okay, we can't execute JavaScript. Why don't we try and overwrite the URL, for example? So we have an annotation that is clickable on the page, and we try to overwrite that URL with something else. So I inject a new annotation. So I break out of the existing annotation array, create a new annotation, give it a URI property that points to an external URL, and then when clicking on the existing annotation, it clicks my new annotation and changes the URL. So we can change the URL. So the challenges I faced in Chrome were all the Acrobat vectors failed, JavaScript didn't even work inside annotations, I could overwrite a URL, but so what? We can change the URL, we don't get the contents of the PDF. So how can we make JavaScript work? Well, this was my first attempt to make JavaScript execution work in Chrome. And as you can see, it requires knowledge of the PDF. It needs an object reference. And the code is huge and really messy. So I thought about reducing it and try to get the smallest possible code required to get JavaScript execution in Chrome. And I came up with this, which is pretty cool. So I break out of the existing annotation, create a new annotation, specify the whole page is clickable, and then I need to use the parent dictionary key to link a form element in order for the JavaScript to successfully execute. So I link to a button and give it a value. So here FT indicates the field type, which is a button, and T is the value of that button, which is A. So this will enable JavaScript execution via PDF injection. So even though I had JavaScript execution via injection, it was good. There was no knowledge of the PDF, which was good, but I was restricted by PDF-Lib, the JavaScript capabilities of what Chrome uses to render the PDF. And I could call the submit form function, but it does not enable me to exfiltrate the document, which is unfortunate. Chrome PDF-Lib does not seem to follow it doesn't have the same functionality as Acrobat, so you couldn't submit the entire contents of the PDF using this function. So I thought, why don't I write another enumerator? I had success last time, why not do it again? So in this case, I wrote an enumerator, did a for loop, used the getOwnPropertyNames function to get all the properties of the object. I created a new array called chunks, and then I pushed all the properties to that chunk because Chrome would only output a certain amount of data. So I put all the properties in chunks and then outputted all of the chunks, and then I found two cool new functions that I'd never heard of. These were get page number of words and get page nth word, which sounds super promising for exfiltrating the text of an unknown PDF. And so this is how to extract text on Chrome. So we create a new annotation, we give it the rect, so the whole page is clickable, we link the button as before, we then execute some JavaScript that captures all the words. So we use get number of pages to get the number of pages in the document, get number of words in the document so we can loop through all the words, and then we can get the nth word by using the position from the for loop, and then alert all the words on the page and extract all the text. So then you could then use the submit form function to submit all the words that you've collected from the page to an external URL. Now, interestingly, the submit form function will only submit to an external URL on a user interaction event. So it requires a click on Chrome. Not on Acrobat, but on Chrome it does. Also, we can use this for SSRF, which is awesome. So instead of creating a button with the FT dictionary, we use the TX dictionary, and that specifies a text field. And then we can use the T dictionary to specify the parameter name and the V dictionary to specify the parameter value. And this is what the post request looks like. So we can control foo and bar. And interestingly, you can use raw new lines. So this means that you could chain this together with other attacks such as request smuggling. So you could do a post request from the injection. And interestingly, this doesn't have a content type either. So that's quite interesting from an attacker's perspective. And this is a hybrid injection on Chrome. So this will work on Acrobat and on Chrome. So first we reuse the existing annotation on Acrobat because Acrobat supports this. It allows us to inject JavaScript, and we break out of the annotation array, create a new annotation and an area on Chrome. So on one part of the document you can click for Acrobat, and on another part of the document you can click for Chrome. So now I'd like to give you a demo of real-time Chrome injection. So here we're using the JS PDF library. Now this is really cool because it shows you the PDF in real time. So the box on the left is JavaScript. It allows you to use JavaScript to define the PDF, and on the right is the generation of the PDF. So this is like an iframe with the PDF content. So first we create a document, then we create an annotation with the X and Y, width and height, and we set a font size and create some text. So now we're going to take our injection and we're going to inject into the input, the URL property, so the input, and that will call alert 1. So we've got JavaScript execution from PDF injection. So this is raw PDF code that's been injected in the annotation and then results in JavaScript execution. I also encountered a HR application that allowed PDF upload. So the HR application allowed you to upload the PDF document, and you could execute whatever code you wanted in PDF code. And I could use this fantastic technique by insert script, where you could read same origin resources, which is really nice. So you can read wherever the PDF is hosted, you can read any URL on that same origin and then send it to an external server. So I tried this attack, but the WAF was blocking the PDF user agent, which was so unfortunate. But I found a bypass. You could use cache resources, and that was not blocked because it didn't go through the server, the WAF. So you could read cached resources on the same domain, which was pretty cool. So to wrap up, PDF libraries should escape PDF strings. This includes parentheses and backslashes. They should always escape these characters when in annotation URIs or in text streams. You can use the injections in this talk to confirm that your code is not vulnerable, and I would consider doing validation on content going into PDFs. I'd like to thank Insert Script for his fantastic talk, PDF Mess with the Web, where he debuted the same origin resource stealing using form calc, which was awesome. I didn't know anything about PDFs until I read and watched Ange Albertini's PDF talk, Let's Write a PDF File, which was awesome, super easy to understand, and that's how I learnt how to write a PDF. I'd also like to thank Ben and Cody for their excellent presentation on SSRF attacks using PDFs, which I was heavily inspired to do a SSRF attack from a PDF injection. I'd like you to take away today that vulnerable libraries can make user input inside PDFs dangerous, Chrome and Acrobat make injections possible, and one link can compromise the contents of a PDF. If you want to read more about this attack, then please visit this site, and I'd like to thank you for your time.